So the citation of Professor Sukhen with us. Professor Sukhen is a distinguished Indian physicist and academic leader currently serving as a senior professor in the Department of Physics at Jadavpur University, Kolkata. Born on July 29, 1964, he has dedicated over 3 decades to the advancement of material science and nanotechnology. His academic journey is deeply rooted in Jadavpur University, where he earned his MSc in 1990, followed by a PhD in 1995, and later an MBA in 2001. This multidisciplinary background has allowed him to approach scientific innovation, focus on both technical excellence and practical application. Throughout his professional career, Professor Bias has become a prominent figure in the global scientific community, particularly in the fields of nanoscience and bio-nanoscience, nanophysics. He leads the biophysics laboratory at Jadavpur University, where he oversees cutting-edge research into energy harvesting and environmental remediation. His work is primarily centered on the development of piezoelectric nanogenerators, multifunctional fluorescent nanosensors, and advanced supercapacitors. Beyond his research, he plays a vital role in institutional governance as a member of the doctoral committee and the physics research committee, helping to shape the academic trajectory of the university's faculty of science. The impact of Professor Bias' work is reflected in his prolific publication record and high citation metrics. With over 270 scientific papers to his name, his research has earned more than 9,000 citations, resulting in a high age index that places him among the leading researchers in his field, according to Nanoscience. His scientific contributions have earned him a place on the prestigious Stanford University list of the top 2% of scientists in the world. Today, he remains a key figure in developing sustainable energy solutions and innovative sensors, bridging the gap between theoretical physics and real-world environmental and biological applications. Join me as I welcome Professor Bias as the next speaker. Thank you, sir.
So, today I will just give some idea about my research work. I am from Jadavpur University, which is one of the best universities in India, and at least more than 45 number of teachers are there who belongs to the top 2% of the Stanford list. Top 2% best scientists of the Stanford list. So I am proud to be a part of that university. So I'm just starting my work. So this is the whole work of my lab. Someday I have seen some patchwork in the hands and legs of one of my students, and this type of patchwork was there. So I asked my student to go there, why this patchwork is there. So we inquire after that, the student tell me that he is from a Bantala, he is from the area of Bantala, that is the Bantala is the leather complex of Kolkata. So my student went there and they found that the area is filled up with various waste material of that leather complex. And not only that, there is a canal, and this canal is, the water of this canal is completely dark. So they called me, sir, we are observing this, what can I do? Then I told them to collect some sand of that area and the water of the canal. They collected that. These are the student, a picture of my student. They collected that, and after chemical analysis, we find that a huge amount of chromium is there. Chromium is a heavy metal, and the huge percentage of chromium is there. It is more than 2.58 ppm. And this chromium is responsible for that patchwork. And then our work is to identify this chromium in the presence of this heavy metal in the water, as well as how we can remove them from the water. This becomes a challenge to us. So we start our work from there. Actually, when chromium is more there, then this chromium, we have seen that with the rainwater, they are leaching inside the soil, as well as in the fruit, in the tree, which is growing there, they are also rich with this heavy amount of chromium. So not only the water, the soil and air, all are contaminated with this heavy metal chromium, and this is causing a huge problem in that area. And this chromium is responsible for this type of disease. It may cause cancer, it may cause lung cancer especially. So what can we do? How we can do the identify this chromium and how we can remove that chromium from there? So this can be absorbed or ingested through our mouth and skin. And not only that, we have seen that your country is also huge contamination of this chromium. And in our country, especially few states are there who are much affected by this chromium. So we started to study the literature, and from the study we find that Boehmite is a clay material which have some fluorescence property, and fluorescence property can be utilized to identify the chromium. So what we did, students after a long study, they identify that the chromium Boehmite can be used, and not only the Boehmite, with the Boehmite, there are some gum, which is called the Acacia gum, which is available from the Acacia tree. This can be used to identify the presence of chromium. How we can do that? Actually, from the picture we have seen, this is the picture of the Boehmite, and I think we will analyze that Boehmite, whether it is pure or not, with the help of X-ray crystallography, and what type of bonding are there. We have done that with the help of fluorescence spectrophotometer, and from here you can see that the Boehmite is decorated with the Acacia gum. There is a dot of the Acacia gum and the broad part of the Boehmite material. And after analysis that, and after that analysis, we have seen that we published the report which we have analysis that we published that in these two papers. And after that, we find that if we make it UV spectrophotometer, then there is the absorption speed at 430, near about 430. If we increase the percentage of Gum Acacia in the Boehmite, actually Boehmite has the absorption at 430 nanometer. And if it is the doping of the Boehmite with the Gum Acacia, then the absorption increases, and after the increases, then it will be very much easier to identify the fluorescence property of the Boehmite. But in that material, if we add the chromium rich water, then the absorption decreases. Now it is easily clear. We have prepared Gum Acacia Boehmite material that have the absorption at 430 nanometer. Then in that water, if we add chromium rich water, then we find that the absorption disappears. That means this happens. Initially, it has a very that is actually we have prepared a Gum Acacia Boehmite and make a solution of that, and that has a very good absorption speed at 30 nanometer. Then if we add chromium rich water, then that absorption will disappear and we will not get that absorption. And from there we can easily identify that the material, if the fluorescence property disappear, then we can easily identify that this material contain chromium mass in a mass amount. Actually, if we expose it with the light of 370 degree 370 nanometer, then we'll get a reddish fluorescence property of like this. Fluorescence property like this. But if we add chromium or chromium content water, then this light will disappear. So if we can find out such a device where this type of fluorescence property will be there, if we make one drop of water which contain chromium, then we can easily identify that the chromium is there or not. So in this way, 0.00025 ppm order also can be identified. It is very sensitive. We can easily identify this order of chromium also. And whether this material is absorbing only chromium or other heavy material, that is why we tested this with other heavy material, but we have seen that this material is only absorbing the chromium and reducing its fluorescence property. This is the thing. Other heavy metal, zinc and iron, chromium, cobalt, nickel, all we have used, but we have seen only chromium it is absorbed. So what is happening there? Actually, when we are 370 nanometer light is falling on this ground state, then some excited electron will go in the upper state and return back, and that is why there will be a fluorescence property. But if chromium we add there, then chromium will contribute with the electron, and that electron will not be able to return back. That is why its fluorescence property will go away, and chromium will be absorbed in that Boehmite material, and when it will absorb in the Boehmite material, it will be there, and if we can remove the Boehmite material from the water, then it will chromium will also remove with the Boehmite material. This is the initial work of our lab, and after that we have also run this with the cell line W by 38 with the cell line, and from there we have seen that this Boehmite material, Gum Acacia content Boehmite material is not harmful for our body, because from the cell line we have observed this also. So biocompatibility test is very important, because we are using to refine the water, and if this water is contaminated again, then it will be difficult. That is why we tested the with cell line. This type of fluorescence property we find when in presence of that Boehmite, we will get a fluorescence property like this. So these are the all tests we have done. Now our interest is how we can make a device with the help of which poor people of that area can easily identify the material, as well as not only identify the material, we can improve the quality of the absorbing property and all these things. Then we start to study a modeling study with the help of the to improve the quality of the material. How we can do that? Actually, Boehmite is available in the form of crystal, well crystalline form. And we know if we reduce the size of the crystal, that means if we can make the nanoform of the crystal, then the surface of this nanomaterial will change. And this is the actual structure of the Boehmite. This is the actual structure of the crystallographic structure of the Boehmite. And this is the X-ray diffraction pattern of the Boehmite. If these peaks are there, then you can easily tell that the material is nothing but the Boehmite. And the intensity and the position, 2 theta angle is position. This is very important for the property of the material. Now, what happens if you can make the nanoparticle of the material? Then the surface area of the material will increase, and when the surface area will increase, then we can tell that the surface material will be responsible for the absorbing of the material. The surface will all absorb very easily from the material. So we start to develop various nanoparticle of the material. Here we can see from the hydrothermal process we have developed some Boehmite material. It is after 12 hours, it is 18 hours, and this 24 hours. And we have seen that the particle size is very small, 3.2 nanometer and 4.1 nanometer and 4.8 nanometer we can get. And from the X-ray diffraction pattern also we verify that this is the X-ray diffraction pattern. It is for the 12, for the 12 is black one, and for the 24 is the blue one. Because as the time increases, the crystal size increases. So as the crystal size increases, the surface area of the material is decreased. And at the same time, we also measure the fluorescence spectrophotometer so that any other bond will make their conduct. And we verify that also on the electron microscope, and we have seen that the crystal size which we have verified on the electron microscope is similar to the calculated crystal size of the material. Then we find out various optical property and electrical property of that material. But our main objective is to find out the crystallographic structure of the material, because whenever any crystallographic structure shifted little bit, then the charge particle, basically any atom is made up of some negative charge or positive charge or some neutral material. And neutral material also exchange some electric and positive charge. So negative and positive charge are very important. And negative charge and positive charge are very important. We get the fluorescence property due to this charge variation. When electron shifted from the ground state to the upper state, from ground state to the upper state and return back, then we get the fluorescence property. So this electron the fluorescence property will go away when the electron will be bound by chromium in the upper state. So concentration of the charged particle in upper or lower state or down state or upper state is very important. So we have to find out the concentration of the charge in various states of the atom. And if you want to find out that, then the most important thing is to find out how the charge is distributed. And if we can find out that how the charge is distributed, then it will be very easy to solve the problem. Then you start to find out the X-ray structure of the material. This is the electron microscope which we have done. And finally, we start to do that in the model study. Then, as I told you, in this crystal, there in the surface, there are much charged particles are there. Whenever the charged particle will be there, they will absorb easily, or they will be able to influence the other. If just if you look into this structure, then you will find that this charged particle, and according to our quantum theory, each charged particle will act as a wave-like material. So this wave-like property will accumulate in some places and will be absent in other places. So we have to find out the charge density at various positions. If we can model that charge density of that material, then you can easily find out how that fluorescence property can be reduced or increased. So that is why we started to study two models. One is crystallographic model and another is DMT, that means density function study. And these two modeling study, help us to find out the actual property of the material. There are the various type of crystal available. And if you look into this material, this is nothing but the quartz or silica. If we trace this upper part will be rich with negative charge and lower part will be rich with the positive charge. As a whole, it is not like that. But when we replace that, when the crystal material, quartz material will be under stress, then the property will be like this. So in this property, you can easily find out that the upper part will be influenced by the negative and negative. Lower part will be influenced by the positive. So that means the charge distribution will be disturbed from the normal position. So depending on the pressure and all these things. So this charge distribution changes very much for the nanoparticle because surface area increases. The crystal which is inside the material is completely bound by the other crystal that don't have any influence of the surface charge. But that surface, if the crystal atom is on the surface, then it is covered in one side, but in another side, the charge can easily move. So the property of the material changes. As we know that depending on the crystal size of the material, gold can be red, yellow, or green, any color. So we measure this and we run this under the deep field condition. What we have done there, we have taken the structure of the crystal structure which we got from the X-ray diffraction pattern. From there we identify the phase and then run the ritual measurement and ultimately we got the final structure of the crystal. But we have measured there. Initially, we got this structure from the X-ray diffraction pattern. From there, we made various types of correction, that is peak profile correction, peak width correction, then the background refinement, scale file refinement, and all this refinement we have done. And when we refine this structure, ultimately we will get the actual structure of the material, and that structure will be compared with the structure which we will get, and from there we will get a crystal structure like this, from where we can easily find out what is the density of the charged particle in the material. So this is the final picture which you get from the after refinement of the crystal. And from there we will start to find out the DMT computation on the forward. That means the density function. Then what we do, we will the refined crystal get the crystal that will get. Then we will find out the supercell, and from there we will use some pseudo-potential, and that pseudo-potential will make a plane with energy cut off section and then keep. What is happening there? Actually, this is the supercell. If you look into this, if this is dope, this is a dope material. That means initially we dope Gum Acacia. Now we are thinking to dope some other material that may be transition material. So if dope this type of material here, then the structure of the material, the property of the supercell will change completely. So we have to find out what type of material we have doped here, and depending on that, how the other active metal, then the property of the supercell will be different. And then, as we know that all charged particle can be used as a Feynman, from the Feynman refinement, you can find that all charged particles act as a wave-like material. So when wave-like material will be there will be a due to potential, there will be a potential and kinetic energy for each charge. If we apply a single potential there theoretically, then if you apply a potential there, then this potential will react with the potential of the charged particle, and from there we can easily find out the what is the surface charge of the material or the density of the charge of the material. And we will get some picture like this. Here, what is happening? The potential due to the presence of the charged particle will be there, and we are applying a potential there. These two interact with each other, and from that interaction, we will get some interactive light like this. And this light, from this light, we can easily find out the band gap of the material, and this band gap is directly related to the fluorescence property of the material, because when the electron will go from lower state to upper state, and it will return back from upper state to lower state, it will emit the energy which it will absorb. And this energy, depending on this amount of energy which is absorbed, which is absorbed or released, the fluorescence color will be different. So from here we can find out the band gap. This two difference is the difference of the band gap. So after doing this type of DFT learning, the modeling test or extracrystalographic test, we find out the ultimately density function. That will, this is the density function, where the density of the charge will be more and where the density of the charge will be less. So after doing this, this is the how this is actually any atom can be represented by this type of equation. This part is the kinetic function, and this part is the potential function, and this is the wave from any charge particle contained in the charge form, and all these things can be represented in the form of the energy. So any atom can be represented in the form of energy, because E equal to mh nu and m equal to mc squared. So we know that mass can be transformed into energy. So any atom can be represented in the form of energy, and when we are finding out the percentage of the energy in actually this is the thing where the density state, where the energy will be more and less. That is directly proportional to the mass of the material. So if you can find out this from there, this is the equation. This is the equation, this is the kinetic energy, and this is the kinetic interaction between the electron and the nearby nucleus, and this is the interaction between the nucleus, electron, and we have to calculate all these things. Okay, we can actually find out the Hamiltonian of each electron, and if all electrons are sum up, you can have this, then we will get the actual intense atom. Next lecture. This number of carbon will be there. Carbon that are called carbon molecule. There are oxygen, carbon, and oxygen. So 66 carbon will be there. Similarly, if for a large molecule, there will be few thousand number of atoms will be there. And if we sum them, then we will get the density of the material only. So this is nothing but the density. So if we find out, then you will find out the density of this material. And this is the density of the side stand is the density of the material. This 2 is only for spin up and spin down. So what is happening? We are applying a pseudo potential, and that's functional part of the charged particle, and from the charged particle we will find the density of the material. Similarly, if we reduce the pseudo potential, then this density will return back to the functional part and it will return back to the pseudo potential. And this may not be similar. It may be similar, may not be similar, depending on the atomic structure of the material. If it is not similar, then a constant part will be there. So we have to consider all these things. And from there we find a graph like this, and from there we can easily find out the band gap and the atomic structure and the density function, density state of the material. If the structure is like this, then the density function will be like this. If the atom is placed here, the density will change, and if another atom is placed there, then the density will change in different way. So now, depending on the doping material or undoped material, the density of the energy will change very much, and depending on the density of the energy, the fluorescence property will change because the energy absorption will change. So these are the similar thing for other materials where the band gap is less than the earlier one. So from this graph, we can easily find out the density. We have published work in a paper. And actually, I am just showing you the paper because if you want to find out the work, then you can search this paper and you will get this. So in this way, density is changing in the material, and I am just going to the similarly, one thing will be there. If it is a conducting material don't have any lower state or upper state. There are three electrons. Then if we measure the density function, then it will be like this. There will be actually conduction band and halide band will be each other. There will be no band gap there. So, depending on the material, conducting material or insulating material, the density function will be different and can be easily find out from there. Actually, we all do this thing just to know how we can, what type of material we can do, which material will give us the proper actual result for us. We have done all these things, and after that, I'm skipping this. You have gone in the earlier stage. We with the Boehmite, we drove two. One is Gallium GD and another is copper. These two we doped because these two materials give us the similar density function of which is similar to the doping of the Gum Acacia in the Boehmite. So we use these two type of material. One is GD and another is copper U, and we find out the crystal structure from there. And we made this is when we add the GD, then if you apply at a dope copper, then the crystals are changing. So we measure all these things, and during this, we measure the fluorescence property of the material. If there is any other bonding or there, the fluorescence property is there. From there, we find out the actual thing we have seen, the similar result what we have seen when we use Gum Acacia, but the absorbance is more. When we apply the chromium, then the absorbance is reducing, and in absence of chromium, the absorption is very high. This absorption property we found in a similar way with the help of doping of the GD. This thing is happening there, and we are making this. This thing is happening. I'm just keeping all these things. I am just going to the final slide of MEAS. These are type of things which we have already measured. And how time changing we have measured also. And I just want to show you this thing. Finally, the help of copper Boehmite or GD Boehmite, we have successfully developed a device like this where in place 1 drop of water, you can easily find out the places from the places format. You can easily find out whether that material contains chromium or not, and if the chromium is there, then the absorbance will change, and depending on the percentage of the chromium present in that water, we can find out the change in the fluorescence property. And not only the fluorescence property, we have measured this fluorescence property with the help of electrical current. So current will change depending on this. And this device is very helpful. If you can use this device in anywhere, you can bring the copper material to remove that from the water. So these are the things which we have done in a short, and this is the thing what I told you. If you give 1 drop of water, then the absorbance will change, and depending on the absorbance, the current will change, and from that change in current, because it is not possible for us to carry a fluorescence spectrophotometer anywhere. So that is why we make a collaborative calibration curve between the fluorescence property and the electrical property. So that depending on the fluorescence property, the current will change, and looking into the current of the material, we can easily find out the chromium content of the material, and we can find out that the material is contained in chromium or not, and from there we can remove the chromium. These are the things that we have. I just want to tell you, this is the conclusion. Basically, being a physicist, I don't have any model, but with the help of model, we finally reached to the goal where we have developed some material, and which material should be doped there or which material should not be doped there, but depending on their atomic structure or density of the charged particle in that material. We measure that first, then we go for the experiment, and we successfully do that work. Thank you very much.